Great. Okay, so I'm very sorry I couldn't come in person. It turned out that my duties as a parent were required here in Waterloo. But I wanted to say a big hello to everyone, and especially to Avi and Lev. 32 years ago, it was 1991, if I've got my math correct, George W. Bush was president. John Major was the Prime Minister in Britain. If you've forgotten who he was, it doesn't matter. Queen Elizabeth II was monarch. John Stuart Bell died the previous year, although he has still had a very strong influence on the quantum foundations community at that time, and of course continues to do so. David Bohm was still alive, and the song "Everything I Do It For You" by Bryan Adams was #1 on the Billboard. Again, if you've forgotten that song, it really doesn't matter. It wasn't very good. I was doing my PhD with Ewan Squires in Durham, in the United Kingdom, and I was thinking about three things in particular. I was thinking about empty waves. I was thinking about Bell's theorem without inequalities because of the GHZ paper, and I was thinking about Lorentz invariance in realistic interpretations of quantum theory. The issue there was, the de Broglie-Bohm model, as everyone knows, is non-local, and this had motivated Bell to ask the question: Do all interpretations have to be non-local, or realistic interpretations at least? Well, the de Broglie-Bohm model also violates the Lorentz invariance. It requires a preferred frame of reference, and so I was asking the same question: do all realistic interpretations have to have a preferred frame of reference or violate the Lorentz invariance in some way? So these are the things I was thinking about, and then Ewan, my supervisor, handed me a preprint that he'd received in the post, and I would say that's when there was this for me, this bolt of thunder from the heavens. This was the Litzer-Weidman bomb testing experiment, and what's so wonderful about this paper is that it's simple. And it's profound. It's really the most simple possible physics you could imagine. There was a prevailing view back then that if what you were doing wasn't in some way complicated, then it wasn't important. And I think that sort of viewpoint still holds sway in some quarters today. But this paper really showed that wasn't the case. You could have a very simple experiment, and yet it was somehow deeply profound. One other thing that was true back in 1991 is that all talks were given on handwritten slides, actually on transparencies using overhead projectors. So I've tried to emulate some of that today. You can no longer buy transparent slides, I don't think, but I have got an overhead projector. So you can find the papers I'm going to talk about, but you can also find my PhD thesis, which is available online. So if you search under my name, PhD thesis Durham, where I did my PhD, then you'll find the PDF for that very quickly. So let me start talking about empty waves. So back in the late 80s and early 90s, lots of people were talking about empty waves. And there were some people who believed that you could detect empty waves in a very simple kind of experiment. So the one I've shown here, you have a source of single particles. You press this button, out comes a particle, hits a beam splitter, and it can go this way or this way. If it goes in quantum theory, we go into superposition. You consider the case where this detector clicks, and then you ask, is it possible that something here is affected? What we want is we want to know which way the particle goes. So we want to know it goes, say, this way, and at the same time that some measurable property of a system which is in the other path is changed. Okay. Well, Franco, he was a wonderfully provocative physicist at the time. I didn't agree with anything really that he said, but he was a lot of fun. He believed that this you could do something like this, but quantum theory says no, and the proof of that is very simple. So you start off with a particle coming along. Initially, this system here, A, is in its initial state, and then the detector D is in the zero state, so it's ready to receive a particle, and then this particle goes into a superposition, and then next either the particle travels along the path U, where it can affect the property of A, so you get D prime, so you get A prime, or in that case the detector D doesn't click, so this is the zero, or you have that the particle goes along path B, and then it causes this detector to click, and in that case there's no change to A, the state of A. So this is just a simple application of linearity in quantum theory, and then you can see that if this detector clicks, then there can't be any change to the property of particle A. So it seems like it's a open and shut case. You cannot detect empty waves. Okay, so here's an interferometer, and Mach-Zehnder interferometer, and we have a source. Particle comes in and go along path U or V. And then at the second beam splitter, it exits. It can go along path D or C. And the way I've set things up, it will always come out on path C. And so detector D will never click. And so the D is for dark. In this case, we'll call this the dark detector. Okay, and there's some trivial mathematics that makes this work. I always use the convention that when a particle is reflected, it acquires a phase, it acquires an I factor. That way, the unitary operators at the beam splitters look after themselves. Okay, so that's straightforward. And then I want to imagine a box plus atom systems. The boxes plus atom system. So you've got an atom. Initially, the atom is in this box here, and it's an atom which is prepared initially with spin up along the x direction. So the state, in terms of the z direction, eigenstates is spin up plus spin down along the z direction. Then what you do is you apply some inhomogeneous magnetic field, and it causes the atom to go to either one side of the box or the other side of the box. And then you partition the box and split it into two. So now you have two boxes, and the atom is either in one box or the other. If it's in the top box, then it has spin up along the z direction. And if it's in the bottom box, it has spin down. Okay. And then finally, you reverse that process. So you remove the partition from the two boxes so they join together, and you reverse the inhomogeneous field so the two atoms come back together. So this is an allowed unitary transformation, and then you go back to the original state. So once again, the particle is spin up along the x direction. So now you put these things together, and John Kramer had this picture in his talk, one of the 36 experiments he showed. What you do is you have the interferometer, and you place the atom plus boxes system so that box A is in path U. And you imagine that this atom and particle have the property that if the particle impinges on the atom, then with probability 1, it causes the atom to get excited. Okay, and remain excited. We'll assume it just stays excited. And the particle is absorbed by the atom. So you can go through the through the mathematics. It's very simple. So initially, the particle comes in. It's in a superposition of U plus V, and the atom is in a superposition of being in box A and box B. And then the term where the atom goes along, where the particle goes along path U, and the atom is in box A. Well, that leads to the atom being excited and the particle being absorbed. And then you have the remaining 3 terms, which are here. So it's three remaining terms where there's no excitation. And then next, you evolve the particle through this beam splitter over here. And if you do that, you get what I have written here at the bottom. And over here, this term here, which I've labeled Elitzer-Weidmann magic, this is the term where it's now possible for detector D to click. And if detector D clicks, then you can see here that you know that the atom is in the state A+. Okay, that's the Elitzer-Weidmann trick. Okay, so that's what we have. So if this detector clicks, we know the atom is here. So how do we turn this into an argument for the existence of empty waves? Well, let me just make some assumptions. So these are some assumptions. If there's only one path open for a particle to reach a certain detector, and that detector clicks, then it is a case that the particle actually took that path. Okay. It seems from a classical point of view like an obvious statement, but when we're doing quantum theory, of course, you cannot be too careful. Assumption 2. Assumption 2 is actually very similar to assumption 1. It's really the same assumption, but for the atom. If at time t, the atom is actually no, I take that back. Actually, assumption 3. Anyway, if at time t the atom state is A+, then this means that the atom is actually in box A, even if we did not make a measurement to establish this. Okay, so this is a bit like the Einstein-Podolsky-Rosen elements of reality assumption. If we know the eigenstate if we know the system is in an eigenstate of a certain type, then we're saying that there is a certain that is a fact about the world in some sense. Okay. And then the third assumption, which is the one that's similar to assumption 1, if the box is closed at time t1, and we establish that the atom is actually in the box at time t2, which is greater than t1, then the atom is actually in the box from time t1 to time t3 when the box is opened. Okay. So if you make those assumptions, then you can reason in this way. So first of all, we know this. We consider the case where this detector clicks. So detector D clicks, and that means that the atom must be in this box. Now, if the atom is in this box, we know that if the particle was to travel along here, it would be blocked. So that means that the particle has to travel along this path, as I've drawn in red. So this means that we know the path that the particle took. It took this path. Now we look at the atom plus box system, and now we can do what I said earlier. We can reverse the partitioning process, so we can recombine those two boxes, remove the partition. And so now, we can make a measurement to see what the x spin is. Make a measurement along the of the spin along the x direction. And now, because the atom is in a spin Z eigenstate, we split up Z eigenstate, it's possible that we'll get spin minus. This wasn't possible previously. So this means that some measurable property in the other path has changed. So we know which path, the path the particle took this path, and at the same time, some measurable property in this path has changed. Now, of course, this kind of argument is subject to believing the assumptions I made, and I think, you know, from the talk that Avi gave, it's far from clear that one should believe those assumptions. They may sort of be fake histories if you take that point of view. So there's definitely those questions. But if you do believe those assumptions, which I think were certainly in the back of people's minds when they were talking about empty waves, then it turns out that using the sort of adapting the Elitzer-Weidmann-Bohm argument, you can do this. Okay. Well, so I wrote this paper up, and then at a certain point after I published this paper, I realized that really this atom plus box system is just another interferometer. This wasn't obvious to me originally. And so one could redraw the essential physics in this way. So this is the overlapping interferometers. And now you can start to ask, you know, you can start to make predictions. So we know that if this detector here fires, well, that means we can reason that this particle must have gone this way because this detector has fired. So in particular, if we place the detector here to absorb the part that would detect the particle, then it is a prediction of quantum theory that if this detector fires, this detector will click. Write that sort of like this. D1 implies, so if D1 fires, that implies U1 will fire. And that's really just the Elitzer-Weidmann reasoning. But this whole situation is symmetric. So if I get rid of that detector, which I can do because I have another copy of the picture over here, then and instead I put a detector here. Then if D2 fires, that means that this detector here will click, U1 will fire. So D2 implies U1 will fire. And we already had D1. What we could also do is we could place the detector in both paths. And now we know, of course, I guess everyone knows this, but I forgot to say it explicitly. This is an electron, this is a positron. If they meet at this point here, they annihilate with probability equal to 1. So now we know that these two particles cannot go through this point. So it means that it's impossible to have U1 and U2 click. And then finally, we can consider the experiment where we have no detectors inside here. So there's no detector here, there's no detector here. Now, if you do the calculation, you can see that sometimes detectors D1 and D2 click. And it's sort of simple to see what that should be the case. If you imagine detector D1 clicks, so the eigenstate for this particle is U2 here, and now this comes to this beam splitter. There's nothing coming along here, so this particle can go randomly this way or this way, and sometimes it will go here. So it's very clear that both detectors should click sometimes. So if you put these predictions together, and you go through a kind of Bell reasoning. You assume that these things are are determined by some pre-existing hidden variables that are shared from the source. Then you get an argument, a version of Bell's theorem, but it's a version which has no inequalities. Basically, every time this happens, then you have a contradiction, which is kind of clear because if detected D1 and D2 click, well, D1 clicking means that U2 would have clicked. D2 clicking means that U1 would have clicked, but U1 and U2 can never happen together. So this is a version of Bell's theorem, and without inequalities. Okay. Those there. But what's weird about this situation is actually, before I go on to that, what's weird, if you want to see the sort of non-locality with trajectories, this is an interesting way of seeing it. So if this detector clicks, then you can reason that I know this particle must have been going here using the Elitzer-Weidmann reasoning. Okay. So this detector clicks, this particle must have been going along here. However, if I instead, in this situation, if I instead put the detector here like this, then in that case, it now has to be the case that this particle goes straight because this Mach Zehnder becomes decoupled, and so it has to come out of here. It's not allowed to come out here. So you can see in some sense explicitly, if you allow these kinds of trajectory pictures, you can see explicitly the non-locality happening. And indeed, if you do a simulation of this experiment using a de Broglie model, then this is exactly what happens as long as the measurement over here happens before this particle enters this beam splitter. Okay. I proposed a quantum optical version of this experiment, and this may be interesting to people. I'm not sure everyone knows this. So here, what you do is you produce a pair of particles. You pump a nonlinear crystal. You have two photons that emerge, and you can arrange it so they have the same polarization coming out. So this is not entangled. This is just a particle comes out this direction, a particle comes out this direction, with the same polarization. And then you have the two Mach Zehnder interferometers like before, but now they meet at a beam splitter here. And then you use the property of beam splitters with photons, which really, because their photons are bosons, that if it's a beam splitter, if you send a photon in to each path and each input path, then the two photons will come out of the same side. So they will either both come out here or they'll both come out here. It's not possible for one photon to come out one side and one photon to come out the other side. This is the Hong-Mandel dip, or the Hong-Mandel dip. So if we look in this experiment, if these two photons are traveling towards this beam splitter, well, this is just like the electron and the positron traveling towards it. And now, rather than the electron and the positron annihilating, they will sort of take themselves out of the picture because both photons will go the same way, either this way or this way. And then in the future, you can tell, because if you have detectors that can discriminate the number of particles, then if you detect two photons over here, you know that they went through this path. And likewise, if you detect two photons over here, you know the photons came through this path. So then all the same reasoning works. If you get a dark count, then you know here, and no photon over here. So you just have one photon on this side, and then it's detected here in the dark detector. Then you know that this detector would click, and likewise on the other side. So all the same reasoning goes through. So that was the sort of work on non-locality, and it's a quantum optical version of it. But going back to the original Maxenter experiment, this one. So now I want to think about Lorentz invariance. This is the third of the questions I had. And if you turn this experiment sort of like this, and now I'm just going to draw the top part of that experiment, which is here. Okay. Then you can think about it like this. So now you consider different hypersurfaces in which you do your reason about this experiment. So here's hypersurface H1. You reason about this experiment on this hypersurface, and this detector clicks. That means that you know that if you did put a detector in here, this detector would click. So and then what you can do, you can say, well, this means that there is an element of physical reality over here, which I'll notate like this, which is that this particle is here. So there's an element of physical reality associated with this region, that the particle is actually there in that path. But instead, you can reason on this path, on this hypersurface here, and consider the case where this detector clicks. And this detector clicking means that the eigenstate goes to this one, and that means that you can, by the same reasoning, say that there is an element of physical reality here, that the particle is in some sense there. And now, if you look at this, then if you look at another way of thinking about this is to look at it on this hypersurface. And now you can say, well, it's impossible to have a photon here and a photon here for both of these particles to be here at the same time. So it's impossible to have U1 equals 1 and on this hypersurface. And so now it looks like you have a contradiction. It looks like it's impossible to reason about this experiment in a Lorentz invariant fashion. And one resolution to this paradox is to say, well, there is a preferred frame of reference, and the preferred frame of reference is the one that you're supposed to reason about elements of physical reality in, and that's the way to get around it. There are other ways of resolving this paradox, and Lev, who's in the audience, has written about this, and Clifton and Niemann wrote a paper on this many years ago, and Goldstein, Durr, and Berndl also wrote a paper on this. So there are ways to think about this, but I still think it's a very significant issue. And it's good to illustrate this with trajectories again. So now, if we reason in the first hypersurface I talked about, H1, so that what happens over here comes first, then we know this particle, this trajectory has to go along this path. Okay. And then this trajectory should go along this path. If we reason instead on a hypersurface where this one happens first, then we will say, well, that means that if this detector clicks, it means that this particle had to be here. So that particle had to go along that path, and therefore that particle had to go along this path. But we're reasoning about the same experimental situation and the same experimental outcome where both these two detectors click. We're just reasoning about it from different frames of reference. And the frame of reference you reason in should make no difference to this underlying ontological situation. So this is, it looks like a very stark contradiction from that point of view. Again, like I said, there's been lots of debate on this and people proposing resolutions. Okay. Okay, well, I actually only have one more slide, and this talk has gone much more quickly than I thought it would. I think because we're in this Zoom format, we're not. I'm not being interrupted by questions from the audience. Let me talk about one more thing I did. This didn't appear in my PhD thesis. This paper came along a few years later, and this is demonstrating the non-locality of a single photon. So Town, Walls, and Collett had written a paper talking about a single photon using this same kind of experimental apparatus, where you send a single photon in here, so the photon goes into a superposition of going this way or this way. So it looks like it's entangled because you have 0, 1 plus 1, 0. And then they had homodyne detect, so they had basically a laser coming in, a coherent state coming in from here and from here. And the coherent state will be the same frequency. So when you detect photons over here behind these beam splitters, you wouldn't know if these photons came from these coherent states or whether it came from the source. And so you're able to do something like a Bell experiment. Now it turned out that particular proposal, there was a problem, and they had to renormalize with some denominators in the Bell inequality, and that relates to this sort of supplementary assumption. So it wasn't a true violation of Bell inequalities if you want to be a purist. But I was very interested in this, and so what I proposed is instead you send in the state 0 plus 1. So you send in here with some coefficients. Okay. And now when it comes out, the state you have on the other side of this first beam splitter here will go into well, the vacuum will just evolve through both sides. But the single particle will now be split . Like so. And there should probably be an I here somewhere. So the state now will have 3 terms. And this is just like the state I showed you earlier with the overlapping interferometers, and also in the system with the atom in 2 boxes. In that case, you would have had 4 terms, but one of the terms has been taken out because of the Elitzer-Weidmann sort of thing, where the bomb explodes. So one of those terms is destroyed. In the case of the overlapping interferometers, the one term was destroyed by the particles, the electron and the positron, being annihilated. Here we have also 3 terms, and now you can have an experiment where you again bring in coherent states from these 2 sides. But also you allow the possibility of placing a detector either here or here. So imagine for a moment you place a detector here in this path. And imagine that detector doesn't fire. Okay, so you have a 0 state here. Well, then that means that the state you have is just the first 2 ones. So this one goes, this one disappears. And so now you have coming over, sorry, it should be 0. Okay. So what you have coming down here, in this case, is Q0 plus plus a term with I1. So you have coming here, you have Q vacuum you have this. So if this detector doesn't fire, so if this detector doesn't fire, then you have this. And so now what you can do is you can have this interfere with the terms that come through here, and you have a coherent state. And actually, all that matters really are the first two terms in that coherent state, which is something like this. So, and you can arrange it in such a way that these things interfere, so that it never happens that you get a click here. So you get one photon here and 0 photons here. Okay, so you can make it so that never happens. Okay, by choosing alpha suitably. Okay. So this is like the this is a lot like the ellipsoid argument. You have an interferometer where a certain output is never seen. In this case, what is never seen is that one photon is detected here and 0 photons are detected there. And now you say, well, what happens if you do detect one photon here and 0 photons there? If that happens, that means the detector placed here will click. So if you have one photon here and 0 here, that means that the detector that's placed here would have to click, just sort of logically, because we've set things up so that if this doesn't click, then that can't happen. Therefore, if this just happened, then this must click. Okay. So we know that if we see a certain event over here, then the photon is traveling along this path. But you can also set it up in the other direction, and exactly the same thing works. So if you detect one photon at D2 and 0 photons at C2, then you can reason, then you know that this detector would click, and you can reason that the particle is going this way. Okay, exactly the same reasoning. And so what that means is, it seems like, and one more thing, it's possible for all of these things to happen. So it's possible to have one photon here, 0 here, 1 here, and 0 here, so that this photon seems to be going both this direction and also this direction at the same time. Now, if you actually place detectors into these paths, then only one of the two detectors will click, because look, well, at most one of the two detectors will click because you only have one photon over here, or 0. So you have exactly the same kind of paradox as before, but now it's utilizing the vacuum state as part of the argumentation. So yeah, so that's those are the things I thought about back in the early 1990s, and it was a tremendous amount of fun. I should also say it was a time when it was very difficult to build a career in quantum foundations, and so I was very grateful to Avi and Lev that they wrote this paper, because it enabled me to write some papers and helped me establish a career. I'm sure many people can relate to that. Things are a bit better now in quantum foundations, although they're not as good perhaps as in other fields. In any case, that's everything I wanted to say. So thank you. I can't hear anyone in the audience.
So which one? So we're unmuted.
Okay.
The problem solution, can you hear us? It's strong enough from here, or we need?
Yeah, I can hear you, Lev, at least. Yes.
He can hear us.
Again. Okay, go ahead. Questions. Okay. Thank you, Lucien. So you several places said that there is this option and that there is this option, and but two together are contradictory, so we have to kind of think what it is and how to. But you know, thanks to Yakir, when we have two-state vector help us, this weak reality, and when we have pre and post selected system, we can say this is true and this is true. Of course, this reality is kind of like quantum reality. You don't have to test this reality strongly, because then you can destroy. But if you look on weak properties weakly, if it's on this path, the weak value is 1, and it many experiments it will show as is. There is a particle there. If you look at another one, then the weak reality is 1, and as is a real particle is there. And if you perform kind of special non-local measurement, trying to test other two together, which this kind of non-local measurement are also in principle possible, and you can also make them weakly. And this weak measurement will say, no, they are not two together. So when we have pre and post selected, and this is the case, you get these clicks which are probable. And every time you get these two clicks together in Hardy paradox, the particle took this way and another particle this took way, but they didn't took two ways together. And in pre and post selected situation, this is the reality. There is no product rule. This projection is correct, this projection is correct, that the product of projection might be different. It's also correct, it's not there. There is no particle here and here.
Yeah, I mean, so yeah, Lev, I mean, I of course I've read the papers. I wouldn't dare to present your ideas but I've read your papers and they're wonderful. Yeah, and I mean, is that? I mean, you think that that's the correct ontological resolution to these paradoxes?
Yes.
Yeah. I mean, I guess I'm still not sure, but it could be. I mean, that could be the correct resolution. I mean, you get some funny situations, but yeah, it could be.
Again, this is funny. It's not acceptable, and the only reason to say that the physics is still okay, if you look on all words together, it's in particular words when you get these two clicks, there is this miracle. But this miracle is only for us. It's not for physics, which takes care of all words together. If you look on all words together, there is all these miracles disappear. There no strange phenomena like interaction measurement or Hardy paradox. They are not there if you look on all words together.
Yeah. Yeah, yes. I mean, I'm aware of the ideas. Myself, I'm still not sure what the correct resolutions to the paradoxes is. I can see that these things work, but I mean, my own point of view on interpreting quantum theory is that this will become clearer when we have a theory of quantum gravity, and then we can hope to get some more clarity. But there are different competing interpretations out there. So, you know, people who pursue the de Broglie-Bohm model wouldn't pursue the ontology that you're talking about. They would say, well, no, there's just this preferred frame of reference, and you have to use the right frame of reference, and then you get the right answers. You know, so there are different possible ontologies. The collapse people, again, they would also not have the same ontology as you, because they're working in a purely forward in time direction. So it's not completely clear, but yeah.
But I think we should see the consistent options, and all what you mentioned are consistent. And I still And then there is taste. What one you prefer?
Yeah. I prefer to wait and see, I suppose.
Other questions, comments, arguments? All.
Lucien Hardy, nice to see you.
I was going to say, I can almost see you at the back. You're behind someone else. Yeah. Hi. Good to see you, Paul.
I'm curious about your comment about thinking that somehow quantum gravity will help resolve things, because certainly none of your diagrams had anything to do with gravity or mass or anything like that. So I'm wondering in what way you think that might be helpful.
I mean, I've been thinking about quantum gravity, not so much in the context of these kinds of experiments. If you look at general relativity, which is a beautiful theory in its own right, then general relativity does suggest its own ontology, and pretty much everyone agrees with the ontology in general relativity, and that's the ontology there is that Beables, people don't normally use that language in GR. The ontology is that the Beables are properties which are invariant under diffeomorphisms, and so that gives you an ontology. And I've been working on the idea recently that that in quantum gravity, Beables would be things which were invariant under quantum diffeomorphisms. So sort of a generalization. In fact, relates to the work of Yakir, who just left. That the quantum frames of reference idea. If you can sort of place that in the context of general relativity, so you have something like quantum coordinate systems rather than just classical coordinate systems like you do in GR, then you can start to think about something like quantum diffeomorphisms and perhaps get to an interpretation of quantum theory that way. So that's an idea that I'm pursuing, but it's not. I don't have anything very concrete to say at this stage.
Thanks, Lucien.
Thank you.
There is a question in the chat, Lucien, if you can address that, would be great.
Yeah. It says, so this is from Alexei Grimbaum. Lucien, is your wait and see more an epistemic attitude than waiting for an ontology? No, I mean, I'm passionate about there being some underlying reality. I think that's something we really need to find. And so I admire anyone who is pursuing something like that. So I strongly admire the work that Lev was talking about. I also admire people working on de Broglie and many worlds and collapse and so on. I think that's something very important. But I'm not convinced by any of those arguments yet. But I think physics absolutely it does have to address this question of ontology. Otherwise, why are we doing physics? So I think if I understand your question, Alexei, I'd say the wait and see is only because I'm excited about what's going to happen with quantum gravity. I think that will maybe settle the question to a greater extent.
Okay, if there are no more questions, let's thank Lucien again.
Thank you.